Hey, Miss Remy.
Hey there, how are you doing?
I'm good. How are you doing?
Good. You joined me like 20 minutes early.
Well, otherwise it's going to be 20 after, and I'll go, oh, shoot, I forgot.
I hear you. I was trying to manage like three calls at the same time. It was super fun.
Well, you do that so well, though.
I don't know. It's it is what it is.
It is.
But it's good to have you here. I hope we'll get some more folks showing up for this.
Yeah,
But if we have a couple minutes, I might go stretch my legs and get a cookie.
go for it. Go for it. I'll hang out. I'll
All right,
moderate
I'll
for
be
a few.
right back.
Okay. Hi, everybody. So Remy went to go stretch her feet or stretch her legs real quick. She'll be back in just a couple of moments. So Remy will be right back in just a couple of minutes. She went to go see if she could run around the block real quick. I know she's fast. I don't know if she's that fast.
Hey, Kathy, this is Ken from
Hey, Ken.
Primus.
Hey
How
there.
did
How are you doing today?
good. How did the rest of the Solar Power International show end up going?
Went really well. It was a busy time, but it went really well.
You know, I think I mentioned this to you, Kathy, there, but I've been going to those shows for, I don't know, 10, 12 so years, and
Uh-huh.
that was, I think, the biggest one I've ever seen.
Yeah,
It, and I think, a lot of it was the Biden's Inflation Reduction Act, the IRA, that a lot of people were motivated to come because they see, a lot of potential there.
sure.
But it was great that it was so huge. It was really great because it was pretty sad after COVID. The first show after
Yeah.
COVID was kind
Yeah.
of pretty much tiny.
Well, that shifted from solar only to RE plus, so it incorporated the other renewables in that space, which is good. I'm sure that helped to broaden the participants, but I know I'm grateful to have had Remy and Aaron there because we couldn't get away from the booth.
Right. Yeah. You guys were, when I was just standing there, it seemed like you had quite a few people that were coming up. I had to walk away so you guys could talk to them.
Well, we could have talked all day, Ken.
That's great. That's great. I'm very happy that you guys were there and happy that the industry is, starting to see some momentum with some infusion of federal dollars.
Hmm. Yeah, exactly.
We just got to get wind doing a little bit. I mean, wind will follow kind of along. I mean, the investment tax credit is also good for wind as well as other renewables. So that's good. So we're gonna see a lot of positiveness as well from the whole thing. But solar is definitely getting the majority of the funding.
Right. Right. That'll be a positive one way or another.
Mhm.
Yeah. Well, Remy, I see you came back from your run around the block.
Yeah, get some hot tea and a cookie for the afternoon, you know?
I'm drinking some hot tea too, Remy. I got a
Yeah.
little bit of a sore throat this
Oh,
morning.
no.
Woke up.
Don't say
So
that.
I got me some throat coat tea. It's like a staple in our house.
Mhm.
Oh, my family is all about the Ricola tea, the Crowther tea that my mom gets us in Germany.
Wow.
And that stuff is like, if you're feeling yucky, it just is heaven on earth. It's so good.
So should I drive up from Annapolis on the weekend and grab some of that from you and then drive home?
You totally should. You're in Annapolis. You're only like an hour and a half. Hey, it's not
Yeah.
too far.
Yeah. Yeah.
Awesome. Well, I want to be cognizant of everybody's time and welcome everybody to the first of the informational webinars. As you might have figured out, we have Ken Kodelik here from Primus Wind Power, who is the people who sent you your amazing equipment packages soon for the second half of you. And so today, the idea is that we will hear from Ken, and he's going to give us the introduction to your equipment package and answer any and all of your questions surrounding what you should do with it and how to do things safely. So the first thing I thought we could do is just go around the room because Ken hasn't met most of you. It'd be nice if the team from each of the colleges could introduce yourselves and in like a sentence or two, sum up what you're hoping to do with the turbine. In terms of your research plan, I know they're still flexible. I think that would help him get an idea of who he's talking to. Then I'll give you some quick updates and then I'm going to hand it right to Ken to get into the nitty gritty. So with that, I guess I'll go down who I see here. And first on my list is Kathy, because you were here like 20 minutes early. So Kathy and Frankie, is that everybody here from NOC?
I think so. So I'll just do my introduction real quick and then I'll turn it over to Kathy because she's the one that's been more active in it. We're with Northern Oklahoma College. We're part of the Division of Engineering, Physical Science, and Process Technology. And Kathy is running a research team with our turbine that includes some of our pre-engineering students as well as our wind tech students, and has also been doing some community collaboration. So I'm going to turn it over to Kathy.
Thanks, Frankie. So my name is Kathy Jackson. I'm in Oklahoma. I'm a adjunct professor with Northern Oklahoma College, and then also a kid wind instructor for the state of Oklahoma and Texas. One of the things that we've been doing as far as outreach portion is concerned is working with, trying to work with Hennessy High School as well as Woodward High School, and trying to bring the turbine space to a garden, an agricultural component they have, which has to do with hydroponics. So they also have other gardening spaces out there. So we're walking the students through the siting process. If the turbine were to go over there, even as a loaner unit, and then how that would work. So, and then of course, siting, you have all kinds of issues that come up or potential issues. So they're addressing those. And then we'll come back to the space of doing the research to answer the questions that have been presented in the project itself, and how to get the answers that have been asked. So that's it in a nutshell.
Awesome. Well, thank you for that nutshell, Oklahoma folks. I saw Joe on here from Donnelly. Do you have anybody else on your team here, Joe?
No, we're in the process of working with David A. Carter who is a director of the Kansas City Energy program, and he does the Kid Win competitions.
Yeah.
And so we're kind of, right now, I'm having my environmental students start to assemble our turbine. And we're going to interact with an area grade school, Resurrection. And then also we're going to work with our high school next door, Bishop Ward. And we're going to host a event that we'd like to do with, in collaboration with Kid Win and David Carter. So, and we'd like to present this at our college. We've already been trying to figure out where we want to put our turbine. We have a couple ideas where it's kind of protected, but it still gets the available wind and things like that. And so that's kind of where we're at this point. And the only other thing is, you sent us some great packets with assembling, and so we're halfway through assembling. I was wondering if there was like a video of the assembly, the particular assembly of the thing that we could just kind of look at as well to make sure we're doing everything right. But other than that, things are progressing.
Ken, do you have something like that, or is this webinar today going to cover a lot of that?
The webinar today, I don't necessarily go directly into assembly pictures, but I do have a few slides on assembly. There's really not a lot of assembly other than just the blade set hub nose cone and then
Right.
sliding the yaw onto the 1.5 inch Schedule 40 pipe. So it's really a really simple process, but I'm happy to do a 10-minute assembly webinar with pictures and everything if that is needed. But and
Maybe
I'm
we
sure
could do that, Ken, maybe we could do that, not at this meeting, but we could set up where you could do that just personally with me to make sure I've done it,
Yeah.
we're doing it right.
yeah, absolutely.
Wonderful.
And we might, there are different hubs and different blade sets you guys got. So
Right.
that's something that we'll need to go through. So
Great.
Okay.
Well, that's all I have. Yep.
That sounds great, Joe. Look forward to hearing more. Did I see the folks from Tidewater Community College on?
Hey, I'm Julie Wyckoff from Tidewater Community College. I'm a mechanical engineering student, and our thought for the wind turbine currently is to mount it as well as some weather data or weather gathering devices, and then trying to use some machine learning to see if we can predict the power output of the wind turbine based off the data we get with sighting the wind turbine and the weather devices.
Very cool. Awesome. Well, thanks for that introduction. Good to have you here, Julie. There's Jim from UMass.
Hello, I don't see any of the other students on here. If they are, feel free to speak up. Currently, they have met with folks in our wind energy center to determine what sort of signals they want to monitor from the wind turbine and external air conditions. And they are looking at, or they're working on identifying sensors that will interface with an industrial controller and then send that data up to the cloud for retrieval. So they're in the process right now of figuring out how they can convert these physical phenomenon like ambient wind speed or vibration of the tower into an electrical signal. We have not received our turbine yet, so we're hoping that'll come in soon.
Awesome. Yep. We have an update for you on that one. No worries. Everything's going to be to you guys soon. Thank you for that one. Todd from Rutgers. Do you have you and your team here? Do you like to say hi?
Hi, so my name is Todd Rossi. I'm a mechanical engineering professor at Rutgers. I invited my students here. I don't know how many of them came. There's 40 seniors in in an alternative energy class that's participating in the project. The class mostly covers wind and solar, so it worked perfectly for this. We're going to install ours on the roof of the engineering building. It's just a convenient place to install it so that the students can access it and work with it. Our research work is going to be first to do some basic wind turbine performance studies, just changing the blades out, looking at the power curves and so on, just to focus on the basics of wind performance. And then the bigger research project is combining the wind with solars and batteries and looking at, you know, optimal control of that, considering various loads that we're going to simulate and utility rate structures and how you would optimally, you know, adjust the charge state of the battery to minimize costs.
Very cool, almost like a model of a larger utility system or something.
Yeah, well, exactly, because we have we sort of have another project that, you know, is more on full scale. So we're kind of looking at this to be a smaller scale of it, and also an educational tool for the students, of course.
That's awesome. Well, thanks for that update, Todd. We have App State represented.
Everyone, my name is Suhad. I'm an assistant professor at the Sustainable Technology and Built Environment Department at App State. And the project now is part of the wind and hydro class. So the students, all of the class are working there with another colleague, but he now has a class, so they couldn't come and join the meeting, but hopefully they'll have the chance to watch that. So our first target is, you know, fulfilling the requirements of this project by setting up the wind turbine. It's going to be off-grid, of course, feeding a mobile lab for our department. And after we monitor it for some time and, you know, have the data ready, we're going to combine. It's pretty much like Todd mentioned. We're going to combine it hopefully with the PV system and, you know, plus of course the storage, like to have a hybrid energy system, which will, you know, hopefully also pour into new, broaden the students' horizons regarding these types of interconnected energy systems. Yes, that's it. Thank you.
Wonderful. Well, thanks, Suhad. That sounds fantastic, and looking forward to hearing more as you progress. I feel like we have, let's see, someone from Santa Fe Community College. Did I see Frank on the call?
You did. Let's see if I can get my camera on. Can you hear me?
We can.
Okay, good. Hi, I am, excuse me, I'm Frank Curry. I am faculty at Santa Fe Community College in our Trades and Advanced Technology Center. I teach in a program called Distributed Energy Technologies. And so I'm actually, we're going to be working with our controlled environment agriculture students. We have many of them. None of them are here right now. They're all in a class. And then we've got some students in a smart grid class. And the idea right now, we're working out exactly how we want to do it. But the wind turbine is going to be integrated into a nested multi-level microgrid. And so it's nominally going to go into what we are using as a remote, a model for a remote aid station. It's going to have a concentrating solar device in there that also produces heat. So there's a battery that's going in with that. And so the wind turbine will be another resource in that. That connects into our greenhouse microgrid, which is slightly larger, about 25 kilowatts in peak right now, that also has its own energy storage system, 100 kilowatt, 85 kilowatt hour system. It's got a tracking PV array, and it's got a natural gas generator coming into it. And then all of that actually is nested into our campus microgrid that we just got an interconnection agreement for, so that we can move forward. And that is the entire campus becoming a microgrid on the Public Service of New Mexico system. And so besides some things that we're going to try to integrate in, and I want to make sure I don't make it too expansive so that we can actually do things, but we've got a data visualization aspect so that students can learn how to take the data that's coming out of various assets and figure out the best ways to visualize that for people. So that's one, data collection and visualization. Another aspect of it is that because we can separate it from the grid, we can operate it, we can look at various operational modes. So we can actually island the system and we can see how it behaves in the context of other distributed energy resources. But we can also plug it into the distribution system and look at the various algorithms that prioritize for different things, from grid services to just letting it run passively. So we're looking at can we use the wind turbine? Well, it's a drop in the bucket for our other systems. It's still measurable. Is this thing going to could we use this for put that energy away and use it for demand reduction? Is it more valuable to let it run passively? And so the students will begin to look at how to prioritize, how to make the project economic, how to exploit the world and the rate structure around it to make it be the most useful. And then wrapped around that is using the turbine in various operational configurations that just depend on what your goals for that project are.
Awesome, Frank. Oh, I look forward to hearing more about that as well. Our last university is the University of the West Indies. Do we have folks representing? I didn't recognize a lot of the names, so. Okay, must just be a bunch of students, but that's fantastic. Thank you guys for those updates, Ken. I hope you found that helpful. And with that, I just wanted to spend a minute or so just giving you guys some updates and reminders from the project standpoint. The first thing, and Ken can talk about this in more detail, but I believe that the second round schools equipment packages should be shipping out this week. On top of that, the power predictors and all the promotional stuff finally arrived at my office. So I will be boxing up things for the teams and shipping those out this week as well. So that's all great news. And from the mentoring standpoint, if you have a mentor already identified, you just drop me an email with their contact information just so that we can include them on future calls if they would like to be there. And if you do not have a mentor still, remind me that you need one. I think we're still working on that for a couple of folks. I know that within the milestones of the RFP, we were supposed to be updating and finalizing our research plans by October 1st. Obviously, that data is come and gone. This is not a deadline or a deliverable. It's a milestone. So it's a recommendation. And at this point, I think if everybody kind of had their research plans updated and finalized by the end of the month, I think we'd all be on a good track for completing our research by February. So again, I'll email you guys these things, but I think we can aim for the end of the month, and just let me know if that's not reasonable. If we want to aim for like mid-November or something. But that's kind of the plan. We are going to be working on putting together a survey for you to share with your local schools to get feedback from them on what a possible demonstration project might look like. As some of you are already working with local schools to build these demonstration projects, so it'll be interesting, but our goal is to get some data that will feed into the next round of this project funding, in which we'll be doing some hybrid system designs for demonstration projects at K-12 schools. And anyway, so that will coming your way in January. And then also just a reminder not to forget that you guys have outreach events planned or proposed. And it sounds like many of you are already thinking about that. And then the last reminder is to please email me if you, especially the students on the call, are interested in being part of the DWS Symposium Planning Committee. So if you're not familiar, the Distributed Wind Energy Association conference is in Washington, DC in February. And we have asked them if we could use their conference as a platform for a student symposium in which you all would be welcome to present the findings of these research projects. So it would be fantastic if a couple of students were interested in helping to be on that planning committee. Okay, so with that, I did want to just kind of tell you a little bit about the power predictors that you are receiving. If you don't know much about them, I will share these slides with you as well. But basically, it's a 3-cup anemometer. It's also got a wind vane, and it also does data logging. These are all of the specs. Feel free to read through the details on it. But just wanted to give you a heads up that this is what you will be receiving. Many of you will be receiving 2 or 3 of them as you have requested. Okay, and then just a reminder that in the RFP, we did ask for some basic performance testing, and many of you have referred to this. I just wanted to remind you what those were. Basically, power curve testing, confirming cut-in speeds, rated powers, cutout wind speeds, confirming that the turbine regulates power when the battery is fully charged, and then some calculations of annual energy production, energy savings and emissions avoided, and then an estimate of how many turbines it would take to offset the energy load of a building on campus or a classroom, knowing that this is a micro turbine and that it is not meant to power your campus. It's interesting to maybe make some equivalents. So with that, I'm going to turn it over to Ken to talk more to you about this equipment package that you have received or will be receiving very soon. And I am going to stop sharing, and Ken, you should have the ability to share your, there you go. Look at you.
All right, can you see my screen okay, you guys?
Yeah, you're in presenter mode. I'm not sure if that matters to you. Where it's showing the next slide.
Remind me in Zoom how to take that off.
I think you go up to display settings up at the top there, okay. And I think you can take it off of presenter mode. Yeah.
Is that better?
Yeah.
Perfect. All right. Thanks you guys. I worked at Southwest Wind Power, so I recognize some of your names. I was the Wind for Schools guy after Ross Taylor at Southwest Wind Power. That was where the turbine was before Primus Wind Power acquired it in 2013. So I was an educator for 10 years myself, a science educator, middle school science educator. So I'm very excited to be part of this project. And so we're going to talk today about, hybrid systems, because that's all we really do. And I'm not going to turn on my camera, sorry guys, just because of the bandwidth issue, and it might be difficult to hear me cutting in and out. So what we're going to do for the next 30 minutes or so is just really brief about history, the specs of the turbine, components, blade sets, applications, give you a little bit of a Wind 101, which most of you probably won't need, but I can just tell you what we tell our customers, which might be interesting to you. Operation installation, how to determine a wind resource, why hybrid is so important, why all of our systems are hybrid, and then end with some installation picks and some examples. This is and some questions, excuse me. This is kind of a generalized webinar today. And as we move forward in this project, I know Remy was planning on multiple webinars. I can get into a much more technical webinar or any other specifics, like we talked about assembly of the wind turbine webinar as well, or we can combine those two together. So happy to do any of that stuff. So just so you guys are aware, we're a USA made product. It's manufactured in Denver. I'm talking to you from Flagstaff, Arizona, where the product was originally built and manufactured in 1995, starting with turbines that we still have out there, the Air 303, then we moved to the 403, then the Air X, Air 30 in 2011, and now the Air Breeze, the Air 40, and the turbine you guys got, the Air Silent X, and we also have another turbine called the Air Max. And so we have thousands and thousands of units out there. And if you ever go to a marina in the United States, typically you're going to see one of our turbines up in a marina. and or a lot of off-grid applications have them, especially if you're in a good wind area like Texas or North Dakota and so on. But the specs of the turbine are real, it's about a 1 meter swept area, rotor diameter is 46 inches, about 1.2 meters. It weighs about 13 pounds. All of our turbines mounted on that 1.5 inch Schedule 40 or Schedule 80 pipe that you should have received or are going to receive. By the way, we're shipping out today or tomorrow, all the schools that were in the second round. Apologize for the delay, but most manufacturers these days have all kinds of parts issues, and we are one of them. So it is a cast aluminum body. You're going to receive a painted version. We call it our marine version, and it's basically an aircraft quality paint, and it typically goes in a marine corrosive environment. You are going to receive 3 different blade sets, or have. One of them I'm going to talk about here in a little bit more is a carbon fiber blade set, and then 2 injection molded black blade sets. You will only be receiving 1 hub. Unfortunately, Remy, we didn't consider that because I didn't realize how many folks were going to be flying these and wanting to fly the different blade sets. So we can talk about getting the other 2 hubs they would need for the Air 40 and the Air X blade set. If there's extra funds, we can certainly do that.
Yep, we can do that, definitely.
Okay, so if they're flying them and they want to use the other blade sets, and we can get into another webinar where we talk specifically about what that means when you use a different blade set on our turbine. So those are kind of just the specs of the turbine. Here's that, the Silent X blade set. It's carbon fiber hand laid. It has aerodynamic trips on there. It's got a fairly significantly different angle of attack than the other 2 injection molded blade sets. It has a specific hub right here. It's more of a locking hub. One of the deals over the years is we learned that when customers would put our blade set on the Air 30 blade hub, it had ability to move. So then they would have to do what we call tip to tip measurements. And if they didn't do it right, it could have balance issues. So we developed this hub where when the blade root goes into the hub, it locks into place and then you bolt it down. So that was a nice advancement we figured out to make things easier for the customer. But you're going to get this really pretty, quiet, and the whole purpose of this carbon fiber blade set is it makes the turbine very quiet, which is what the customers want these days. They do not want a turbine that is loud. So this is about 40 decibels or less, whereas our Air 40 blade set, the black blades are about 65 decibels. And then the Air 30 blade set is well over 100 decibels. And when you're flying this stuff, you'll begin to realize all this. So the 2 turbines, the basic difference here, our land units have a gray cast aluminum housing, and our marine units have this white aircraft quality paint, which I just described. Here's those other blade sets. So here's the blade set, is from about 2011 or so. We developed this one. This was the original blade set that goes back to 1995. And so you can see it's significantly more surface area on this blade set, which gives it a little bit lower startup speed, and it makes it work a lot better in lower winds. So when we're talking about a low wind speed environment, this blade set generally is the one we sell to customers. And it's about 65 decibels in sound output. When we have an industrial site like telecom, oil and gas, we typically sell this blade set to customers. It's got a higher startup speed and only really produces a lot more power when you get into the higher winds. And it's designed that way. It has a specific control algorithm for that particular turbine so that it is designed to work in a high wind speed environment and produce as much current output as possible, as much power as possible in a high wind speed environment. So different blade sets, different turbines for different wind regimes and different customers. And here, of course, is the carbon fiber. So we have this spreadsheet that we show our customers of the 6 different turbines we have. They all come in the 3 flavors, the 3 voltages, what our applications are, what our markets are, the wind regime, and the sound output. And all of this is very important in the real world when we're talking about people buying wind turbines from us. And so we try to, this webinar is recorded, and I try to get every customer who wants to buy a turbine from us to take this webinar so they understand what they're getting and why they're getting it. And so we go through this in detail. We also talk about how the turbine works. So the customer, a lot of our off-grid customers, are very hands-on. Most of them install the equipment themselves. So they need to know how the turbine works. So just real quickly, it's an upwind horizontal access turbine, meaning this is the wind direction. And so you have the nose cone on the hub, which you'll see when you do the assembly. And the nose cone is important to have on there for a number of reasons. A lot of you guys, I understand, are engineers and so on, but it helps to reduce the turbulence across the face. Aesthetically, it makes it more pleasing. It also helps to reduce any water infiltration that might infiltrate through the rotor shaft bearing gap. That is when you slide the rotor onto the hub, onto the rotor shaft, or the hub onto the rotor shaft. We do have 2 bearings in there. Here's your face. It has a stator inside. That's the copper windings. And then this is your rotor, which has neodymium magnets surrounding the outer edge of the rotor. 12 neodymium magnets, and that rotor slides into the stator. The blade set spins, turns the rotor, and that's what produces the electrical charge. We call it wild AC, and that's what is outputted from the stator, wild unregulated AC. Then it goes into a circuit card, which then regulates that wild AC into regulated output of 12, 24, or 48 volt DC power, which is what comes down tower. All of our turbines are voltage specific. So that's why you guys told Remy what voltage your system was going to be. And I want to make this really, really clear, because this is a huge a thing that we tell our customers is the voltage of the turbine has to match the voltage of the battery bank. And you can see on the yaw sticker of your turbine that will be coming or is there, this is the yaw, and there's a yaw sticker that says what voltage your turbine is. It has to match the battery voltage. If you want to switch voltages, then you have to change out this stator and this circuit card, which gets very expensive. So that's why we asked specifically what voltage your system was going to be. In here, there's a potentiometer and a LED light. I'll talk about that a little bit more in a second. This is your yaw bearing. This is your slip ring assembly, which allows the turbine to rotate or yaw 360 degrees without the wires getting crossed up. And then this is the yaw, which is what mounts onto the 1.5 inch pipe. That's a 1.9 OD, 1.5 ID. And then 3 wires, a positive, negative, and a ground down to your battery bank. Here's a standard hybrid system line diagram. So I want to just review this really quickly with you guys. I understand probably most of you guys understand this or know it, so I apologize for those who do already. But a basic PV array here, you go through a charge controller, you have your ammeter, your battery disconnect, your fuse, your breaker, and that goes down to your battery bank. On the wind side, it works simultaneously with the PV, but it's autonomous from the PV. The only thing you're coinciding with on the PV side is battery voltage. Both the PV and the turbine are always looking, the charge controller specifically off the PV, are always looking at battery voltage. And our turbine is doing the same thing. And so you run the positive and negative through a stop switch, a fuse, a breaker, an ammeter, and you have that. That's called your wind control panel. That has a stop switch, a breaker appropriately sized for your turbine, and a digital meter, all in one nice little box to make wiring easy for you. And then that whole system goes into your battery bank. In that wind control panel, there's a battery in and a wind turbine in. And you're just going to run those 2 wires in into that wind control panel, and then out to your battery bank. And so it makes things relatively easy. So both the wind turbine, as I said before, and the PV charge controller are looking at battery voltage, and they're doing that all the time. A couple reminders is that when the wind is blowing but the sun is shining, the solar is going to be pushing current, which is going to be increasing battery voltage, right? And if it goes above the regulation voltage set point of the turbine, then the turbine will shut down, even if it's windy, because that's what it's designed to do. I'll talk about this a little bit more in another slide, but that's called the regulation voltage set point. And you can see that turbine shutting down in high wind conditions when the sun is also shining. If you're interested in this diversion load controller and resistive load design, for sake of time, I'm not really going to talk too much about it now, but you can dump the power from the battery bank and keep the turbine below the regulation voltage set point by using a diversion load controller. And Morningstar makes one called a TriStar. There's a Xantrex C40. There's a number of options out there. And then you dump that into a resistive load like an air heater or a water heater that can then use all the additional power that would generally go into the battery bank and dump it through a diversion load. That is an option. I would say most of our customers don't do that because it adds complication. But if you want to learn a little bit more about that, I'm certainly happy to talk to you about it. When we're talking about batteries, the minimum battery bank size for an Air Silent X 12-volt turbine, which most of you guys got, is 400 amp hours. So keep that in mind when you're sizing your system. If you're just doing testing with the turbine, maybe you're gonna use a resistive load or some kind of dump load, then you can go smaller. But if you're gonna let this run, if you're gonna fly the turbine and you're gonna let it run out in the field, you need at least 400 amp hours. We can talk more about that later on, or you can ask me specific questions. Here's that potentiometer. All of our turbines have this regulation voltage set point set at the factory. Here are those set points. It is adjustable based on what kind of battery bank you have. Some sealed lead acid batteries and certainly lithium ion batteries require a certain set point, so you can adjust it, which is you do using the mechanical pot screw. This is a potentiometer screw on the side of all the turbines. I apologize for these pictures, but here's the pot screw and it is adjustable. And you can see here's the adjustment range and how you turn to adjust it. We did receive an NREL grant to have Bluetooth technology on our next turbines coming out in late 2023 and 2024, that you'll be able to do all this with Bluetooth technology. Unfortunately, we're not quite there yet, but so right now you do it with this screw and a flathead screwdriver. That's what that is. Also, you notice on the belly of your turbine is an LED light. This LED light is an indication of what's happening with your turbine. Here's a really important thing. When you first install your turbine and connect it to the battery, you want to look for your initial 2 blinks, and it's a red LED. And once you get the turbine connected and you know that it has a good connection, no wire issues, you're going to get 2 slow blinks. Or if you hit your stop switch, if you flip your stop switch from stop to run, you're going to get 2 slow blinks. And that'll say that, hey, battery's connected. I see you. The circuit card sees you and is activated. When your turbine starts to spin up above about 500 RPMs, then you'll start pushing current, and this LED will then illuminate solid, and it will be solid while you're pushing current in amps to your battery bank. If it starts blinking slowly, that means your turbine is in regulation. That's the point at which your battery bank is full and the turbine says stop, and it'll apply the electromagnetic brake through the stator and the circuit, and it'll slow the RPMs down to below that minimum 500 RPMs needed to produce current. And the light will begin blinking, and it will not push current to your battery bank to overcharge your battery bank. That's how the turbine works. It's on or off. It's a bulk charger. It does not have the same finesse charging that solar does. Absorb, float, equalize, all that stuff that solar has. Our turbine is a fairly basic unit, and it is a bulk charger. It is charging or it is not charging. That charging level will vary based on the wind resource, obviously. If it's, 8 miles per hour of wind, you're going to be pushing less than a half an amp, micro amps, or if it's 35 miles per hour wind at 12 volts, you could be pushing, 30 amps. So it's variable based on wind speed. The last indication on this LED is a fast blink. A rapid blink means the turbine is in overspeed protection. That means the turbine RPMs have exceeded a specific amount based on the control algorithm built into the turbine, and it will apply the electromagnetic brake, and it'll slow down the RPMs of the turbine so it doesn't spin out of control. It's overspeed to protect the turbine for long-term reliability. So that's a fast blink. Here's the wind control panel you just got. This is a 3-position, single pole, brake before make, stop switch. So it breaks the circuit going between run and stop. It goes through open circuit, and then you go to stop. Never leave this stop switch in the middle position. That's open circuit. That means the turbine will spin up, try to push current, and then shut down. It'll do that until the circuit fails. So always in run or stop. Here's your breaker, appropriately sized for the turbine and the voltage, and your amp, and this is your digital meter, gives you voltage, current in amps, power in watts, and energy over time in watt hours. There's a little button right here that you can reset your watt hour meter, and you just do that very easily. It's with a little push pin in there, and you can reset it. So you're all getting a digital meter. We have a lot of really great videos on our website that you guys should check out, especially the troubleshooting video, which goes through how to look at all these modes of the LED, how to push current through your turbine in a test situation. That's the first video on this website right here. So if you go to our website, primuswindpower.com, go to the support tab, go down to maintenance and service, you'll be able to see those videos. It would be a good thing for your students to check out, as well as a lot of other interesting videos. So check that out. Let's talk a little bit about tower height. And generally speaking, with a micro turbine, most of our customers don't go more than about 35 feet. Our tallest tower, our tallest guide tower we sell is 45 feet. Oil and gas, telecom, sailing customers, their turbines are usually 12 to 15 feet. So our micro turbines are generally low because they're relatively inexpensive, and the cost of towers is expensive, and wire and all that. But you can see from this diagram that as you go up in height, you get out of the surface roughness of the ground, and your power production increases. So the higher you can go up, obviously, you guys probably all know, the better, more power production you're going to get out of the turbine. But with a micro turbine, like I said, it's all about costs and how you figure that calculation. What's more important than tower height is really sighting. And you can see from this diagram that you always want your turbine on the prevailing wind side of any object that's going to cause turbulence, like a tree or a building and that sort of thing. I heard Todd at Rutgers earlier said he's going to do a roof mount, which is fine. We have a lot of customers who do roof mounts on their energy sheds or their barn and so on. But a few things you got to remember about roof mounts is that you're gonna not achieve the power curve because there's a lot of turbulence, and you can see that based on this diagram right here. If you're mounting that turbine on a, like in this plateau mesa idea, you're going to get vertical turbulence coming off the vertical faces of the building, and that's going to certainly hurt the power curve. The killer of wind power is turbulence. So the best place you can put it is on the water or some open area, grassy area, where you have a large area between the turbine and any object that's going to cause turbulence, like you see in this coastal picture. If you have it on a rooftop, as you know, as a ridge top or some kind of small mountain or hill, as the wind comes up the hill, it begins to compress, which increases velocity, which then will help that wind turbine to produce more power. But buildings, not so much. We have a rule in wind. We call it the 2250 rule. Again, that's 2250 for micro winds, specifically 20 feet above or 250 feet away from any object that's going to cause turbulence. That's what we recommend. To be honest with you, most of our customers never achieve 2250. Because the turbine is so inexpensive, they're just hoping to get additional power in the winter months from that turbine, and therefore they're happy generally with what they get based on the wind resource they have and where they can put it or site it. We're going to talk a little bit about the hybrid system. A lot of this you guys already know, but this is, we're all about selling wind turbines. We're a business, right? And so your students need to know how we sell and why we sell, in my opinion, my humble opinion as an educator myself. But this is why hybrid systems have been extremely successful for us as a business for many years. And I started pushing this concept back in 2013. And now, quite frankly, it's really been adopted by the renewable energy industry across the world. Not that I did that, but hybrid systems are really the buzz, the talk. There's a lot of talk about that at SPI in September at the Solar Power International show. And here's why. Solar is great. I have it on my house in Flagstaff, Arizona, but it does have low output in winter months. It has diminished output in bad weather, and obviously no output at night. So wind power helps when obviously in the winter months, you tend to have a higher wind speeds in the winter months. The air density is higher in the winter months, as you know, based on the wind power equation, which includes density, velocity cubed, and swept area. That's how big your rotor diameter of your blade set is. Wind on average is better during inclement weather. When you have bad weather coming in, you generally have wind. We have a lot of data from various data sites that we can prove this. And that's what we cite to our customers and so on. And wind does frequently blow on those long winter nights. If you've ever been in Cheyenne, Wyoming in the winter, you absolutely know that. And that's how we sell our systems. Hybrid systems make sense. And this is kind of a vision, a picture that helps represent this to our customers. Not a lot of wind in the summer months. You can see here represented by the orange curve is solar. The blue curve is wind, but you have a lot of wind, a lot of weather in the winter months. So you're doing a lot better in the winter months. So all the heavy lifting in the summer months is done by your solar system. You're generally producing 80%, 90% of the power for your system in the summer months, but then you're getting a lot more input to that battery bank in the winter months from the wind turbine, because generally you're going to have more power coming out of that wind turbine. It's the complementary nature of solar and wind. This is how we sell wind turbines. This should certainly be communicated to your students, and it's our business model. We have a good wind resource across our country. As you can tell, the darker the blue color, the stronger the wind resource. A lot of blue here in the mid portion of our country, right? We sell a lot of wind turbines in this area. We sell a lot of wind turbines on the coast and on the East Coast. A lot of mountaintop wind turbines. That's what all these little islands of dark blue are. These are telecom sites that we sell to. Telecom people buy our turbines a lot because they help support their off-grid remote telecom sites. And so this is a general idea that there are a lot of wind places in the country where there's a lot of wind. But how do you determine that wind specific to your site? Well, we have a free system that we offer to our customers, as well as we're going to offer to you guys through AWS True Power. And what customers do is they send through our website their address or their decimal data coordinates or their GPS coordinates to me or to our general email, info@primuswindpower.com. And we send you then a wind resource assessment of your site. And it's really good data. It's as low as 10 meters of tower height and 200 meters of resolution. So if you are thinking about putting your turbine at your particular site at your school, I'm certainly happy to provide you with a wind resource assessment of that particular spot. So send me the decimal data coordinates of that spot, and I will have myself or one of my team members send you this wind resource assessment. What we generally recommend to our customers, if they're going to be installing a hybrid system, is 4 meters per second or greater of winter wind. So that would be November, December, January, and February. Those are the months we care about, because those are the months when your solar is going to be doing the worst. And so that's how we sell and describe our systems based on 4 meters per second of winter wind. Here's kind of what a system or a wind resource assessment looks like. It's multiple pages, and it has a wind rose, and it has a monthly distribution as well. And this is my house in Flagstaff, and you can see here that it's 14 meters. This is the tower height, 45 feet, and an average wind speed of 3.71 meters per second. But what I look at generally is the winter months, right? So I would be on the cusp, on the edge of whether it makes sense. Plus, obviously, I have a lot of turbulence, quite a few trees, ponderosa pine trees in my yard. So that's something I consider. You also get this wind rose. This is really a power rose, right? It tells you where the power of the wind is coming from. So something to consider when you're siting your wind turbine. This is what we provide to our customers so that they can do a better job of putting their turbine in the right place on their property. Here's another site. You can see it's on the water. This is the pin where the turbine is. You can see it's open to the prevailing wind direction on the water. And so very good site, much higher wind resource, again at 14 meters of tower height right here. And so much higher wind resource. And so that's what they're going to get, or you would get, or our customers would get when you're deciding where to put your wind turbine. So go ahead and use that resource as needed. So when we talk about hybrid systems, it's all about the battery bank. For our off-grid customers, and for you guys as well, even during testing, you've got to consider the battery bank, trying to keep those batteries happy. And in our world, with lead acid or either flooded or sealed lead acid, this doesn't apply for lithium, right? But for flooded or sealed lead acid, we recommend no more than a 50% maximum depth of discharge from that battery bank. That's the off-grid rule. Maximum 50% depth of discharge. When you start going below 50% on a flooded or sealed lead acid, which is still the majority of our customers, to be honest with you, lithium is really taking off, but it's still the majority of our customers have flooded or sealed lead acid battery banks. That's really where you need to be, because below 50%, the sulfation rate of that battery begins to obviously be a huge factor. So how we sell is based on the fact that if you can add wind to your system, make it a hybrid system, there's a better chance in the winter months when you have the least amount of solar that you can keep that battery discharge level more in this 30 to 40%. This is a Trojan battery brochure, and you can see based on this curve, you have a lot more cycle life. That's basically how long your battery is going to last before you have to change it out. In this 30 to 40% depth of discharge rate. So that's how we sell. We say, look, your batteries are going to be happier. You're going to save money in the long run. And anybody who knows off-grid is going to tell you that changing the batteries out is the worst part of an off-grid system. Your genes get corroded. They're very heavy. generally. So, and they're very expensive. So if you can keep those batteries happier, that makes a huge, huge difference. So it's about extending and maximizing battery life. That's how a hybrid system works. You guys, I have about 4 minutes left, and I'm going to just show you some quick pictures of just some systems that we've put in over the 25 years we've been doing this. This is how we started off-grid cabins. Some of you guys might remember, some of you older folks like me might remember, I'm 55, but when solar was $10 a watt. And that was the heyday of wind. That's when Southwest Wind Power was selling hundreds and hundreds of wind turbines every month, because we could produce a wind turbine a lot cheaper than solar cells at $10 a watt. Now we're 50 cents a watt. So big difference, right? So this was an off-grid cabin. This was our primary business, along with a remote site like this, second and third world countries, just getting them a little bit of power in a remote site. We also did a lot of marine sailboats who, again, don't have a lot of real estate to put solar on their boat, but they do have vertical real estate. So we see 1 and 2 turbines on their boats to produce power for their off-grid system on their boat. Hybrid systems that incorporate parking lot lights. Just to be honest, I didn't design this, but this causes a lot of turbulence, right? As you can imagine, up onto that wind turbine. This was not a very good design. So I use this as a not a good example of a hybrid lighting configuration. We do a lot with oil and gas, oil and gas has decided that wind turbines make a lot of sense in their off-grid sites, and they buy lots of them because they just make sense. They save them money. These are remote systems for various sites, disaster relief and deployment, and all kinds of other sites where they put these on that pallet, which then they bring in and set at a site. It's about 600 watts of solar. You got your batteries in here, your charge controller. This is a Roan 10-foot section of self-supporting lattice tower. And then the pipe slides down, and this whole assembly slides down. And so it transports very easily, and then they put the turbine on top. So it's a pretty cool system for all kinds of oil and gas sites, as well as disaster relief and deployment. Different portable trailer systems on mining ponds and tailing ponds. This is Antarctica. You can tell by the vertical solar panels here. But I do want to point out that at some point, if you decide to get another wind turbine, you want to consider the downwind shadowing effect if you're going to put your wind turbines fairly close together, which we have lots of customers who buy 2, 3, 4 wind turbines at a time. And we talk about this idea of here's upwind, right? Upwind, the blade set is upwind. So you can see this turbine is at a different elevation than the turbine in front of it to minimize the downwind shadowing effect of the upwind turbine. So something to consider if you ever put 2 turbines at a site. Here's another idea of that. This is a NOAA buoy, and they have 2 turbines at different elevations as well. This is telecom. We do a lot with telecom. Our turbines are used on mountaintop sites all over the world and in second and third world countries where the grid is not really accessible, coupled with solar. Do a lot with positive train control. That's been in the news a lot, especially the last years, where they have these remote sites. They used to power them up with propane generators, and now 90% of the power comes from solar and wind at these remote sites. Here we do a little bit with RV. I just like this picture. This is a palapa on the Sea of Cortez, but we do have some RV stuff as well. And of course, remote sites in Alaska and very harsh conditions all over the world. So there, that's 12 o'clock. My time is up. Hopefully you guys can stick around for a few minutes for questions, but I do appreciate you guys listening, and we can get into more of the technical aspects of the turbine or any other topics you want to explore in a later webinar. And again, thanks for your time today.
Ken, that was amazing. Thank you so much. I hope that that was helpful for everyone. I will let it open up to questions, but I'm also going to pose a question as you're asking them. is what you would like to see as the next informational webinar topic now that we've done this. But I know, Soad, you look like you're ready to ask a ton of questions.
Yes. Actually, first I say thank you very much, Ken, because he already answered some of them. But there's another couple of questions. Yes, and I'd love some, just a little bit of confirmation regarding some steps.
You may want to turn your video off because you're breaking up. I can't hear you unless Remy, you can hear her.
No, I'll turn mine off too. It looks like we might have lost Sohad. So I don't know if anybody else has a question while we're getting her reconnected.
So Ken, Joe, I don't know if can you hear me?
Yeah, I
Yes.
can hear you, Joe.
So we were thinking about putting our, we have the smaller one that has a platform, and we were thinking about putting it on a ledge off of a balcony. And I'm thinking maybe that's not going to be such a good idea because it's kind of facing southwest where we get prevailing southwest winds. So I'm thinking maybe that's not going to be such a good idea. Probably maybe I would rather have it on the ground somewhere. We have a grassy commons area, and then we also have a fenced in foosball field that we could put it inside there and just move it whenever we needed to. But it's kind of, there's another building that's kind of situated, but we get a lot of wind. It's like a little wind tunnel through there. So I'm not sure about that, but I can probably send you some images of our property and we could figure it out.
Well, Joe, by far the easiest place would be put it on a building because
Put it on the what?
put it on the building.
Oh, yeah.
But you'll just need to know that that's gonna reduce the power curve and the power output of your turbine.
Right,
What that number would be, I don't know.
right.
Calculations out there probably based on vertical face and blah, 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 but that is the easiest solution. If you put it in any other place, you're gonna have to get some kind of a tower system for it.
Right.
And guy wire towers are the cheapest, but most schools hate guy wire towers. So, and monopole towers are very expensive. So those are things you have to consider. And up on that building.
Yeah, is it possible to like it's got the feet that's come out. Is it possible to put 4 different sandbags on the feet to hold it in place?
The demo tower is not designed really, you're talking about the demo tower, Joe?
Yeah, we have
Yeah.
I think it's.
Yeah, that pipe with the demo
it
tower
has
is
a
specifically
shorter
for-
stand and platform feet that stick out.
Right, that's specifically designed for a classroom application. It's
Okay.
not designed for actual building mount systems. So here's a rule of thumb.
Yeah.
That everybody should be aware of. You can go 9 foot unsupported with a Schedule 40 pipe. You can go about 12 foot unsupported with Schedule 80 pipe. When I say unsupported, I mean without guy wires attached to it. So if you wanted to mount it on that building, Joe, you would just mount it to the side wall of the building using some mounting brackets.
Right.
We sell a roof mount kit that has all that, that a lot of people use, but a lot of folks do their own thing too. And you could go with a Schedule 40 pipe 9 foot above the last mounting bracket. With a Schedule 80, you can go 12 foot above the last mounting bracket. If you go to our website, go to the support tab, go to manuals and downloads, you'll see the rooftop mounting kit. And I have some pictures and so on in there of some of that. So hopefully
Great.
that was helpful.
Yeah.
Awesome. These are all great questions. And I did, if no one else is thinking about it, Ken did talk a lot about how he can utilize the AWS True Power data to get you a wind resource analysis for your site. And since that is kind of one of the basic research questions that we've asked everybody to address, Ken, you probably should plan for all 8 of these folks giving them to you, even if they're not planning to actually fly the turbine. They will want to have that data to do some theoretical analysis anyway.
Well, Rami, I have a question. I'm sorry for
yes.
that. It was a glitch in the net and, I went off everything. So regarding the power testing, so what is exactly required? I mean, do you need, for example, do we need to monitor or record temperature, or whatever is provided by Power Predictor is enough?
Yeah, I mean, so the basic research questions that we posed, and again, nothing is quote unquote required, because you guys are getting your grant money up front, and then we just trust you to do great things. But the idea was to verify the power curve, to collect some, verify the cut-in speed and the cut-out speed and the rated wind speeds and things like that. So most of it is going to be data that you can collect through the display that Ken has provided in their packages, right, Ken?
You mean the turbine demo stand?
No, so they can get voltage and.
Oh, the wind control panel.
Yes.
Yeah, that gives you, right, that gives you current and watts and watt hours and voltage and all those 4 parameters.
Yeah, so most of the research questions that we're posing can be answered with the data, with the equipment that you are receiving. And all you have to do is figure out how to put it in the wind. So wind tunnel, strap it to a truck, drive the truck around, so there shouldn't be needed extra equipment, but we will send the power predictors, but the power predictors only have wind data. They do not have temperature or humidity or anything
Because
else.
we can buy a site, that's why I'm asking. So if it's,
Yes.
Critical, or you don't, because, not every researcher goes through the temperature, especially for wind, but
Right.
but it indicates, the density of the, wind. So at some
Yes.
point it might be. That's why I'm asking, do you need that or not? So I can plan ahead for purchasing something and putting.
Not necessary, but if it's part of your research question, then go for it. But
Okay.
in terms of the research questions we posed, it wouldn't necessarily be required.
Can I ask another question?
Please.
Thank you. This is for Ken. So Ken, thank you very much for the wonderful, really, presentation. It answered a ton of my questions, but regarding the charge controller. So I know it's different for a PV system and for the wind turbine, and there are some that can do both in the market. So what's your advice?